Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at structural isomerism. We're going to talk about what structural isomerism actually is, why molecules can exist as isomers, and explain the terms chain, positional, and functional group isomerism with examples. Before we talk in detail about structural isomerism, it's important you are comfortable with what we mean by molecular formulas and, more generally, organic chemistry. Molecular formulas show the number of atoms of each element in a given molecule. For example, the molecular formula H2O shows us that one molecule of this substance, water, contains 2 hydrogen atoms and 1 oxygen atom. Organic chemistry is the study of carbon-containing compounds, apart from carbon dioxide, carbon monoxide, and carbonates. Organic molecules typically have a backbone made of carbon and hydrogen atoms, and may also include other elements such as oxygen or nitrogen. Recap done? Let's go! Sometimes 2 different molecules can have the same number of atoms of each element, meaning they both have the same molecular formula. When this happens, we describe the molecules as isomers. Specifically, if they have different structures, they are called structural isomers. For example, the molecular formula C4H9Br can refer to several different molecules, all with the same number of atoms of each element, but with the atoms bonded together in different ways, giving different structures. There are sometimes lots of different ways the molecules can be different, meaning, to be more specific, we further describe structural isomers based on the types of structural isomerism they show. These are referred to as chain, positional, or functional group isomers. Chain isomers are structural isomers that have a different length carbon chain as their carbon backbone. The carbon backbone in a molecule refers to the longest sequence of carbon atoms bonded together, creating a chain of carbon atoms. The carbon backbone can vary in length and structure, sometimes forming branched arrangements where carbon atoms bond in different ways. This means molecules can have the same number of carbon atoms as each other, however the carbon backbone can be different, depending on how the carbon atoms and groups are arranged. For example, the molecular formula C4H10 can refer to 2 different molecules. In the first, butane, the carbon atoms are bonded together in a direct sequence or chain, meaning the carbon backbone is 4 carbons long. In the second, however, 2-methylpropane, the carbon backbone is only 3 carbons long, with a CH3 group bonded to the middle of the 3 carbon atoms. These would be chain isomers of one another. Positional isomers are structural isomers that have a particular group bonded at different positions in the carbon backbone. For example, the molecular formula C5H11Br can refer to lots of different molecules. But 3 possibilities would be a 5-carbon backbone with a Br, a bromo group, bonded to one of the carbon atoms. In the first, 1-bromopentane, the bromo group is bonded to the first carbon in the backbone. In the second, 2-bromopentane, the bromo group is bonded to the second carbon in the chain. And in the third, 3-bromopentane, the bromo group is bonded to the third carbon. These would be examples of positional isomers, the same type of molecule, the same carbon backbone and functional group, but with the group attached at different positions along the chain. Functional group isomers are structural isomers that have their atoms bonded in a way that give different functional groups or types of molecules. A functional group is the part of a molecule that determines its chemistry and how it reacts. It isn't just the type of atoms in a molecule that can determine its functional group, but also how these atoms are arranged. This means molecules with the same molecular formula can have different functional groups, depending on how these atoms are all bonded together. This type of structural isomerism can be the hardest to understand and see. For example, the molecules propanone and propanal both have the molecular formula C3H6O. However, each has a different functional group. In propanone, there is a carbon-oxygen double bond in the middle of the carbon backbone. This gives a functional group of a ketone, whereas in propanal there is also a carbon-oxygen double bond. However, this time it is at the end of the backbone, given a functional group of an aldehyde. A more complex example would be something like propanoic acid and 3-hydroxypropanal. In propanoic acid, there are a total of 3 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. In 3-hydroxypropanal, there are also 3 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. This means they have the same molecular formula, C3H6O2. However, these are clearly 2 very different molecules, and they would both have different chemical properties. The functional group of propanoic acid being a carboxylic acid, and the functional groups of 3-hydroxypropanal being a hydroxy, OH group, and an aldehyde. They are therefore functional group isomers. So, to summarise, structural isomers are molecules with the same molecular formula but different structures. Chain isomers differ in the length of the longest carbon chain, or backbone. Positional isomers have the same functional group but at different positions. And functional group isomers have different functional groups. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.